In today's video, we're going to be revising the topic of forces. As always, this video is applicable to all exam boards, and without any further ado, let's start having a look at our first topic, which is Newton's second law. Now, this is actually the defining equation on what a force is. Newton's second law says that the net force is equal to the mass times the acceleration for a constant mass. So we can say that the net force is equal to F, which would mean that this will be equal to ma, where once again F is the net force, the mass is given A, and the mass is given the letter m, and the acceleration is A. Now, what exactly do I mean by net force? Imagine that I have a little box over here, and let's say that I have 1 Newton acting downwards. If this was the only force acting on this box, then the net force in this case will be equal to 1 newtons. Now imagine that I have a box and I have 1 Newton acting downwards, but in this case I also have an equal but opposite force acting upwards. The two forces will cancel one another, and now the net force will be equal to 0. Of course, I can have a case in which, let's say that I have a force of 1 newtons acting downwards, and let's have a larger force acting upwards. Let's say that I have 2 newtons acting upwards. In this case, the net force will be equal to 2, take away 1, which is equal to 1 newtons in the upwards direction. So we can just write this down. Now, what unit are we using? The answer is a Newton. What exactly is a Newton? The definition of a Newton is a very, very important one. And as always in physics, when we're defining units, the trick is to think about the equation and then substitute the number 1 for each of the values. So the Newton is defined as the force required to accelerate a mass of 1 kilogram by 1 meters per second squared of an acceleration. Now that we have a basic idea of what a force is, let's have a look at a few different types of forces. So first off, starting off with the weight. Now imagine that we have an object which is falling towards the ground through space, and that's the only force that is acting on that object. The force due to gravity is known as weight, and it has a value of mg, where m is the mass of the box. So the force is going to be called W, and this will be equal to mg. And this will always be acting vertically downwards. So I can say that this here is always acting vertically downwards. G on Earth is equal to 9.81 meters per second squared. So the weight will just be equal to the mass times G. It's really important to know that all objects, regardless of their mass, will always experience the same acceleration of 9.81 meters per second on Earth. Okay, now imagine the object wants to fall, but there's some sort of a support on the way. So this could be the earth, it could be a table, it could be the floor of a building, it could be a number of different things. We still have the force due to gravity, the weight acting downwards, that's still not disappeared. So the weight, which is equal to mg, is acting downwards. But now the net force is 0 because this object is not moving. So there has to be an upwards equal and opposite force. This here is the normal force N. Now, fundamentally, this is an electrostatic force. It's due to essentially Pauli's exclusion principle, meaning that 2 electrons cannot occupy the same space at the same time, and this force will always be equal and opposite to gravity, assuming that the surface is level. Okay, well, let's have a look at upthrust. So upthrust, let's say that we have an object which is submerged. So let's imagine that, let's say that we have something like some sort of a water over here. So I'm gonna try and be creative with my drawing. Now we have a box which is quite buoyant. Depending on the density, the upthrust can have a different values, but let's say this is something which is quite buoyant, so the box will have its weight acting downwards, but it will also be experiencing an upthrust due to its submersion in a fluid, and we typically give that the symbol U. If we have an object which is being pulled up by a rope, for instance, this could be through some sort of a pulley system, or maybe there's a helicopter is pulling up a load, or something like that, or an electric motor, then, but if this here is a rope, then there will be a force of tension like so. And let's say that if we have mg acting downwards, the tension will have to be bigger. Now, what is friction? Friction is a force that is opposing motion. So let's say that I have an object which is moving this way. Well, if the velocity is going this way, there will be a force of friction. So let's say we're pulling it with a force F, but there will also be another force due to friction. Typically, we give that lowercase f, which is always opposing the motion. Okay, well, these are some of the basic type of forces. Now, all of these diagrams that I've drawn here are actually examples of what are known as free body diagrams. A free body diagram simply is a way of showcasing what forces are acting on an object. Typically in a free body diagram, unless it's a sketch, we'll need to have the forces in the correct proportion. So for instance, if I had, let's say, 1 Newton acting to the left, and let's say that I had 2 Newtons acting to the right, then notice that the length of this arrow is twice as much as the one going to the left, and in this case this will allow us to determine that the net force in the horizontal direction, so I can just write this down, the horizontal direction is 1 Newton, and that is 1 Newton, and that is acting to the right. Similar to projectile motion, the forces in the horizontal direction are independent of the forces of any forces in the vertical direction. Okay, so let's apply what we've learned so far at a little problem. We have a helicopter which is lifting a mass of 100 kg at a constant velocity. What we need to do is find the tension in the cable. Okay, well, imagine that this here is our mass. What forces are acting on it? First off, we have the weight, which is acting downwards. We're also going to have a force of tension. Now, the next bit is really important. Let's do that in a different color. But anytime we have constant velocity, this statement, constant velocity, means that there's no resultant force, because if there is a resultant force, there's going to be acceleration, because F is equal to ma. So constant velocity means no acceleration, therefore no force. Kind of think of it as F is equal to ma. If a is equal to 0, F will also have to be 0. Okay, well, let's go back to solving this problem. Helicopter is lifting the mass of 100 kg at a constant velocity. Find the tension in the cable. Well, if there's no acceleration, so I can just write if a is equal to 0, the net force is equal to 0, which means that the magnitude of the tension will be equal to the weight, which means that the tension will just be equal to mg, which is going to be 100 times g is 9.81, which is about 981 newtons. Let's use a couple of significant figures, so I'm going to leave it as about 980 newtons. Okay, well, the second one, the force is now increased and the load experiences an acceleration of 1 meters per second squared. Find the new tension in the cable. Okay, well, the net force is going to equal to the tension take away the weight. So the net force is just the sum of all the forces. Because this force is acting upwards, I'm going to be taking this to be a positive because we're moving in this direction, and the other force is going downwards, so I'm going to take that to be a negative force. So the net force is equal to T minus W. Remember that the net force is also equal to ma, so mass times acceleration is equal to T minus W. Therefore the tension T will be equal to ma plus the weight. Okay, well, the total mass is just 100 times the acceleration of 1 plus the actual weight, and the weight is just going to be 100 times 9.81. Well, this will just be equal to 981 plus 100, which is just 1081 newtons of tension. Okay, well, what we've done so far is we've looked at Newton's second law, we looked at free body diagrams, different types of forces, and we've applied this to a problem. Now let's have a closer look into one specific force which is known as drag. The acceleration is typically not a constant during the motion when an object is experiencing a drag force. Now typically we're going to have a look at this experiment more carefully, but you might have a long tube that is, let's say, filled with some sort of a viscous fluid, and you might have a little ball bearing that is traveling downwards. If the ball bearing has a weight, let's say W, it will have a drag force which will initially be quite small, but as the object is picking up speed, eventually the two forces are going to be equal and the object will be reaching terminal velocity. So as the object is going down, the drag force is increasing. And it increases quite rapidly because drag force is proportional to the velocity squared. There's some factors that affect the drag force in air and in a fluid as well. It's dependent on the surface area, and it's obviously dependent on the speed as well. Now let's examine the motion of an object that is falling through a liquid. Once again, this could be a ball bearing that is traveling along a long tube in a fluid, in a viscous fluid, like so. It could also be the motion of a skydiver, for instance, as well, that is falling through the air. So initially, at that very first instance, when the ball bearing has dropped, or maybe our skydiver has fallen down, so we can try and draw a little skydiver. Let's not forget the parachute, like so. So as soon as they fall out of the plane, their acceleration is g. So the acceleration is g. So that initial gradient here will be equal to 9.81. Now, as the time goes on, the drag force will be increasing, which means that this graph here will be starting to curve because the acceleration will be decreasing. So right here, the acceleration is decreasing because the drag force is picking up. So in the case of our skydiver, initially, let's label this number 1. We're just going to have the weight mg, which is acting downwards. Now in our second point, let's say this here was the first, let's say our point 2, then we're now going to have a couple of forces acting. So let's draw a skydiver yet again. So my drawing is kind of getting worse and worse, but this here is our skydiver, and now they have 2 forces acting on them. So they have mg, which is acting downwards, but we also have a drag force which is not quite equal to mg. So in this case, the net force is just simply equal to mg minus the drag force. Now right over here, you're going to notice that the velocity is constant. So in our third region, we have terminal velocity, like so. So at terminal velocity, the 2 forces are equal to one another. So let's assume that our skydiver is just this point. Then in this case, we're going to have mg acting downwards, and we're also going to have the drag force being equal and opposite. So our drag force is equal to mg, meaning that the net force is equal to 0. Let's have a look at some practical skills with regards to the investigation of the motion of, let's say, a ball bearing in a fluid. So first off, we need to fill a tube with a viscous fluid. Then we could drop a ball bearing, so we can just draw one over here. Now, as we're dropping our ball bearing, what we need to do is we need to mark consecutive equal intervals on the tube. For instance, every 10 centimeters. So every 10 centimeters, we could draw a little line like so, approximately like so, and each of those distances is 10 centimeters. Then we're going to drop the ball bearing, and we're going to record the time it takes to reach each interval. So at what time did it reach this interval, at what time did it reach this one, this one, this one, this one, and so on and so forth. We're going to take multiple readings and then find the mean. Now also I'll make a note that we can use a magnet. So we can use a magnet to retrieve the metal ball bearing, like so. And we're also going to be ensuring to be using a long tube in order for the ball bearing to actually be able to reach terminal velocity. By probably the middle of the tube, we'll realize that the time it takes for the ball bearing to pass through each interval will be very, very similar, and the ball bearing would have reached terminal velocity. In fact, if we're to plot a graph of, let's say, the speed against time, we're going to get that familiar curve of the acceleration decreasing and then reaching a constant value, and this constant value just here is our terminal velocity. This is quite a good way to be investigating that. Now let's revise the forces on a slope. Imagine that we have a standard box with a weight mg. If this is sat at an inclined plane at an angle theta, first off, the normal reaction will be at 90 degrees to the actual surface. So this angle here is a right angle at 90 degrees. The weight will be acting vertically downwards. We can actually split our component of the weight to a component which is parallel to the plane, and we can also find a component which is perpendicular to the plane. So let's do that using some simple trigonometry. First off, if the angle here is theta, then we can say that this angle here will be 90 minus theta. Well, hang on a minute, let's use a different color for this. We can split the component of the weight as a component which is perpendicular to the plane, which is this one over here, and also a component which is parallel to the plane. Let's just use a more contrasting color. So I'm going to use this one over here. Well, the component which is parallel to the plane can be found using some trigonometry. Remember, if this angle here is 90 minus theta, because this angle here is theta, meaning that this angle here will be 90 minus theta, but this angle here is also 90, meaning that this angle here will have to be equal to theta, like so. Okay, well, using the knowledge that this angle here is theta, what we can say is that the component parallel to the plane is the opposite of the angle theta. So we can just say that the parallel component will be sine theta mg, or we can just say that as mg sine theta. Similarly, the component which is perpendicular to the plane will be mg cos theta, because that's just the adjacent component, which is just this one over here. And we have successfully split the weight into some parallel components and some perpendicular components. I have an in-depth video on this, and I'll provide a link to the description if you were a little bit confused about the angles. If you're not confused though, it's always worth remembering that in this scenario, the component which is parallel to the plate will be the weight times the sine of the angle, and the component which is perpendicular to the plane will be the weight times the cosine of the angle of the plane. Okay guys, next up is the concept for the center of gravity. Now, what is the center of gravity? It is a point at which the entire weight of an object seems to act. This point, the center of gravity, can be the geometric center. So if something is, let's say, spherical, the center of mass will be the center, assuming that it has an even mass distribution. If something though is, let's say, shaped like a donut, then the center of mass will be somewhere in the center, even though there isn't a let's say some physical atoms in the center. So right over here, even though there's nothing, the center of mass will still be, in this case, the geometric center. The center of mass is can be very, very similar. Essentially, it's a point where the entire mass of the object seems to act, whereas the center of gravity is where the entire weight of the object seems to act. Remember, the two are just connected by F is equal to mg, okay, which I can just write that down once again over here. Okay, well, how can we determine the center of mass? So we can determine that using a practical. So first off, I'm going to pin an object, and then I'm going to hang a little plumb line vertically downwards, just let gravity do its work. Then I'm going to rotate the object and pin it at a different point. So I've already done this over here in my little diagram over here, and I've produced 3 different lines. You can probably do that with 2 as well to determine the center of gravity, but the more the better in this case. And the intersection of those lines is the center of gravity. So in this case, this over here will be the center of gravity. So guys, let's take a moment to talk about moments. Now, the moment of a force is defined as the product of the force and its perpendicular distance from the pivot point to the line of action of the force. Now, this is quite a lot of words, but first off, let's understand what a moment is in our own words. Now, imagine that you have a seesaw like this, and let's say that we have some sort of a force F, maybe somebody sits down. Well, what's going to happen to this seesaw? We immediately know that there's going to be a turning effect, and the whole seesaw will start moving in this direction. Now, depending on which way the seesaw will be moving, we can say that we could have an anti-clockwise moment. So if the whole thing is moving in the anti-clockwise direction, we'll have an anti-clockwise moment. So I'm just going to write anti-clockwise. But on the other hand, if we had, let's say, a force which was being applied here, let's call that F2, then the seesaw will turn in the other direction, which is the clockwise direction. So let's just make a note of that. And if that's the case, we would have a clockwise moment. Now, what exactly though is a moment? Let's have a look at our definition. So it is defined as the product of the force. Okay, so far so good. So we can say that a moment, I'm going to call that M, is equal to the magnitude of the force times the perpendicular distance from the pivot. Well, in this case, our pivot is just here to the line of action of the force. Well, the line of action of the force is just an imaginary line along the force vector. So this over here is the line of action of the force. Let's call that distance, for instance, x, and in this case the moment will be the force multiplied by the distance, which is x. So once again, we could have a clockwise moment or we could have an anti-clockwise moment, and the moment of a force is defined as the product of the force and the perpendicular distance from the pivot point to the line of action of the force. Okay, well, now let's apply our definition of the moment to a situation in which the force is not perpendicular to the pivot. So in this case, I have something like a shelf which is held together by a piece of string, and let's say that this string exhibits a force of 5 newtons. Now, what is the moment of this force with respect to this pivot? Okay, well, as we have defined, the moment of the force is equal to the magnitude of the force times the perpendicular distance. I'm just going to call that x. Now, once again, x is the perpendicular distance from the pivot to the line of action of the force. Now, the line of action of the force is just here. So what we need to do is we need to take our pen and then essentially just draw a perpendicular line from the pivot point to the line of action of the force such that there's an angle of 90 degrees. So we're going to draw a line here such that this angle here is 90 degrees. Now we can use some trigonometry to find our perpendicular distance x. Okay, well, let's use, for instance, the fact that sine of 30 is equal to the opposite divided by the hypotenuse. So our opposite is equal to x, our hypotenuse is 0.2, which means that our perpendicular distance x will be 0.2 sine of 30. But hang on a minute, sine of 30 is just a half, so x will just be equal to 0.1 meters. I can just write this down over here. Okay, well, this means that our moment for this force will be equal to 5 newtons multiplied by the perpendicular distance from the pivot point to the line of action of the force, which is just 0.1 meters times 0.1, which will be equal to 0.5 Newton meters. The unit for a moment, by the way, is Newton meters because it is just force multiplied by a distance, the perpendicular distance from the pivot point to the line of action of the force. Okay guys, next up is the principle of moment. So this is a really important definition or principle in moment. So let's take a moment to appreciate it. First off, an object will be in equilibrium if there's no net force acting on the object. Otherwise, there's going to be an acceleration. Number 2 is that the sum of the anti-clockwise moments is equal to the sum of the clockwise moments. For instance, the seesaw above will only be in equilibrium if the force times the distance for the anti-clockwise moment. So in this case, it's going to be F times X. This is all of the anti-clockwise moments is equal to the sum of the clockwise moments, and in this case this will be F2, and let's say that this is at a distance x2. So this is only true if F2 times x2 is equal to fx. Should we just be consistent and just give them some subscripts? I'm just going to call this one f1 and x1. But the sum of the anti-clockwise moments is equal to the sum of the clockwise moments. And this is our principle of moments. Additionally, we could also say in an exam the principle of moments that there is no net moment, and this will also be accepted. Okay guys, now let's revise force couples and torque. What is a force couple? A force couple consists of two equal and opposite forces which are acting in the same plane. For instance, if we have two forces, let's call them F1 and F2. These will form a couple if they have the same magnitude, but they're acting in the opposite direction. So F1 will be equal to F2 in magnitude, but opposite in direction. Now, torque is defined as essentially the net moment. Let's say that those forces are separated by a distance d. The torque, which is given this Greek letter tau, is defined as the magnitude of one of those forces, let's call it F, multiplied by the distance. So assuming that F1 is equal to F2 and that's equal to F, so the torque is equal to the magnitude of one of those forces multiplied by the distance between them. If an object is in equilibrium, we can use a commonly used technique known as the triangle of forces. So this is true only if the object is in equilibrium. So we should know that only if the object is in equilibrium. Okay, well, how does it work? Pretty simple. I'm going to start with one of my forces. Typically, I choose the weight, which is acting straight down, and I'm just going to draw my weight, which is acting like that. After that, I'm going to draw the normal reaction, which is going to be acting a little bit to the left. In fact, because this forms a 90 degrees triangle with this surface, let's say that this here is at 30 degrees. If that's the case, well, the angle between the weight and the normal reaction will also be 30 degrees. It's kind of like the same triangle that we looked at before when we were resolving forces on a slope. So if we're at 90 degrees here, let's go down 30 degrees and we'll be able to draw our normal force, which will be along here. Let's draw just a little bit shorter. Okay, so this here will be our normal force, and our normal force will actually be pointing upwards. Let's call that N. The final force that we need to draw is obviously the force which is acting upwards, which will be the force F, and let's draw this with this angle here being 30 degrees. And this is the correct triangle of forces for this particular situation. We have the force F acting to the left, we have the normal reaction N acting upwards, and then we have the weight acting downwards. Okay guys, we're doing extremely well. We've revised a lot of material. This is a long topic. Now let's have a look at density and pressure. Remember, the density of an object is given the symbol rho. This is just the Greek letter rho, and density is defined as the mass per unit volume. The units of density, because of that, are kilograms per meter cubed, and pressure is defined as the amount of force per unit area. They're both scalar quantities. So because of that, the units of pressure are newtons per meter squared, and this quantity is also known as the Pascal. Okay, now the next derivation about pressure is incredibly important, and as the equation for the pressure inside of a fluid. So imagine that you have, let's say, a tank of water, or maybe you were diving in the sea. What will the pressure be at a height h? So as we said, the pressure is equal to the amount of force per unit area. Now, if I had a diver somewhere over here, the amount of pressure that will be exerted will be equal to a cylinder of water above the diver's head. Well, this will be equal to the mass of the water times the gravitational acceleration on Earth divided by the surface area. Well, hang on a minute. Mass is actually equal to density times volume, because density is just mass over volume, so just rearranging for the mass. So I can just plug that expression in here. So what I'm going to get is density times volume times g over the area. Now the volume of a cylinder is equal to the area times the height times g, and now I'm going to be dividing by the area one more time. Well, now I can cancel out the area, and I'm left with an expression for the pressure at a height h to be equal to the density of the fluid times the height times the gravitational acceleration. And this here is an expression for the pressure of a fluid at a height h below the surface of a fluid. Finally, let's revise Archimedes' principle. So Archimedes' principle states that the upthrust acting on a body submerged in liquid is equal to the weight of the liquid that has been displaced. So if I was submerging a sphere in water, what forces are acting on it? First off, we're going to have the weight, which is just mg, where m, of course, is the mass of the sphere. We're also going to have an upthrust, which will be acting upwards, like so. Depending on the density of the object that's been submerged and the density of the fluid, this upthrust could be bigger than the weight, and if that's the case, the object will float upwards. If it's smaller than the weight, the object will sink. If they're right about equal, such as the two drawn, then the object will actually float. Now, Archimedes' principle once again states that the upthrust is equal to the weight of the liquid that has been displaced. Well, let's say that the upthrust is equal to the weight. Let's say that this is water, just to keep everything simple. So I'm going to say that this is equal to the weight of the water. Now, the weight of the water is just equal to the mass of the water multiplied by g. Now the mass of the water is just equal to the density multiplied by the volume that has been displaced, so the upthrust will be equal to that. Now let's say that an object has a generic area A and a height, let's say x, or it could be h. Then the formula for Archimedes' principle is best summarized by those two equations over here. That the upthrust is equal to the density multiplied by the surface area multiplied by the height times g. Okay folks, well this was a very long video in which we covered most of what is required, in particular in year 1 A-level on forces. Hopefully this video was useful. If you have found this video useful, please consider giving it a like and subscribing. Thank you very much for watching, and I shall see you guys in the next video.